Hey, how you doing? Welcome to Live Force Review. Let's see if I can't get my. There we go. Got my deal all set. Got my deal all set up. Okay, turn down the sound on my. Turn down the sound on my phone so that I can see the live chat. Forced. You're right. You are definitely forced there, John Torres. Okay, so like we said in class, I need you guys to give me some specific questions. I will start off with a generic problem of the K and L variety, and then I will take questions. If we have questions, I will keep going. If we run out of questions, I'll stop. Ideally, this will be somewhere in the neighborhood of a half an hour, so you don't have a whole lot of time to ask me your question. Okay, so to involve everything all at once. I'm just making these up as I go along, but so let's get started. Okay. Ramp, like we do. Block, like we do. Let's say 30 degrees. I don't know how clear that is. 30 degrees. Okay, let's set that on autofocus lock so it doesn't do that all the time. Let's try that one more time. Whatever. Close enough. Anyway, 30 degrees, let's say mass of 25 kilograms, okay? Let's say an acceleration down the parallel to the block face, let's say 2 meters per second squared. Yeah, there we go. What is the mu k in this situation? Okay, so we have our angle, we have all of our knowns. Let's get started. Now, first things first, let's do our free body diagram. We have normal force going that way, we have friction force going this way, and this was just for demonstration at first. So we have Fk. Touche, look at that. Okay, let's see if I can refocus now. See if that works a little better. Can y'all read that? It drives through the focus and then goes crazy. There we go. Weird little tricks. Good call, Taylor. Okay. Anyway, got it all fixed. So we have our incline block. We are drawing in our free body diagram. That's Fg. We have F normal, and we have mass, acceleration down the block, mu k, and our angle. So let's get started. We're going to start with calculating our Fg. That's just our mass times our acceleration due to gravity. Okay, so 25 kilograms times 9.8 meters per second squared equals. Okay, so what's your question, Adam? Okay, exit. What's the first thing we do when we start using this thing? That's right. Check and make sure that it is in degree mode. So 25 times 9.8 equals 245 newtons of gravitational force working on this guy right here. Next, we're going to calculate our F parallel and our F perpendicular. We draw a little fake triangle. We have this guy, which is F perpendicular, and this guy right here, which is F parallel. This is a lot like the example I just loaded up on my website earlier today. So if this one leaves you a little bit mystified, feel free to check that one out. So F perpendicular is equal to our Fg, and it's our adjacent side to that angle. So it's Fg times the cosine of theta. And similarly, our parallel is the same deal, but with sine. So let's go ahead and calculate that bad boy out. 245 times the cosine of 30 degrees is 212.18 newtons. And our F parallel is 245 times the sine of 30, or 122.5 newtons. Okay. We should remember this method from our projectile motion. Okay, right there. That's our parallel right there. It looks like F11, but it's parallel right there. Okay. So we have these things. Now let's figure out how we're supposed to use them. So let's add up our forces perpendicular. Again, I have a little bit of more experience with these things, so I know this is where I need to start. But even if you started with the other, you'd still end up with the right answer if you took your time and worked through everything. So F perpendicular. Our forces working perpendicular are our normal force pointing this way. See that right there? And then our force perpendicular pointing into the block. Okay, so why is the acceleration parallel? Mostly because I defined it that way. I said at the beginning of this problem that the acceleration is along the face of the block. That was just a condition, initial condition given in the problem that I just made up. So not for any other reason. But also, you'd expect the block to accelerate as it slid down the ramp along the face of the block. Anyway, so back to our summation equation. F perpendicular equals Fn, and because it's in an opposite direction, minus our F perpendicular. And that's going to give us m times a. That's just always a result of our summation equation. But let's go ahead and say that there is no acceleration in the perpendicular direction. My box is not shooting up off that ramp, so our acceleration is 0. That means that m times a is also 0, and if I add F perpendicular to both sides, we end up finding out that Fn is equal to F perpendicular. And of course, their magnitudes are the same, they're in different directions, but we can go ahead and write that in there. Okay. Now, almost running out of space. Let's check. Okay, so let's do this one over here. Now, let's add up our parallel forces. Okay. Now, our parallel forces are just, let's call Fk negative, right? So our F parallel minus our Fk equals our mass times our acceleration. Okay. So we know our F parallel, we're calculated up here. We know our acceleration and we know our mass, which means we can solve for our Fk. All right. So our acceleration, we already set up here, is 2 meters per second. We know our mass, which is 25, and we know our parallel force. So let's go ahead and do all that stuff. 122.5 newtons minus whatever Fk turns out to be equals 25 times 2. Okay, so let's go ahead and move this over here and move Fk over that side. We're just combining like terms and working out our math. We end up with Fk equals 122.5 minus 50, or 72.5 newtons. Okay, that's our Fk. But that's not what I asked for in the beginning of this problem, is it? It's our mu k. Now, okay, so Jada, can I say that perpendicular force is always equal to the normal force? Now, there are very rare situations when I would say that always is a thing in physics. Certain things like that are time is always positive, mass is always either 0 or positive, but no, I don't feel comfortable saying that the perpendicular force is always equal to the normal force, because, I mean, this isn't part of this problem, but let's imagine that that instead, I have this inclined thing and I'm also pulling in this direction. In this case, we'd have the force of the box pressing in, but we'd also lose some of that force as being pulled up out of the box. See? So like if we had a force pulling the box away from the ramp, then this force right here, which is part of force of gravity, would not be equal to our normal force. So let's just say no, that I don't feel comfortable saying always in that regard. Good question though. Okay, so I need some space. All right, so our equation for calculating our mu k, because that's actually what we're looking for in this whole guy, is this guy right here. You'll recognize this from our equation wall on the side of the inside of the classroom. Fk, we've already figured out where our Fk is, so that's 72.5 equals whatever our mu k happens to be, multiplied by our normal force, 212.18. Divide both sides by 212.18. And our mu k is equal to, what is that, 72.5 divided by 12. 0.34, yeah, 0.34. There we go. Answer to this question. Bingo, bango, Dunskies. Cool. All right, any questions before I get rid of this one? Okay. Okay, because I only have 10 viewers on here, and I feel like I made a rather impassioned speech for my live stream, let's go ahead and say that the first 10 people who come into class and say this word to me get an extra 3 points on their test. Okay? This also means do not tell other people. All right? I'm talking about the first 10 people who tell me this phrase from the moment I walk into school. All right? So if 10 people do it first period, then that's all that happens. If 10 people do it second period, whatever. If 10 people do it third period, however. The first 10 people. So don't go texting this or telling anybody else who isn't watching this, because then they will take your points, okay? Plus 3 points right here in writing, so blah, blah, blah. Get at it. Okay, and John, part of the point is so you can review this. And like I said, I actually posted today another problem just like the one we just did. So you have 2 now that you can look at, okay? Okay, so let's do a L level problem, okay? So we like to do those elevator ones, so let's do an elevator one. Okay, so elevator. Okay, so elevator held up by 3 cables. And we have force of gravity pushing down. And because they're held up by 3 cables, each one of these is going to be F tension. Now, in this case, F tension of 1 is equal to the F tension of 2, and that's equal to the F tension of 3. Unless we say something different. I'm just stuck with mu k. Okay, yeah, we can do a mu k in a second. Think of a problem and ask me when we're done, and I can get at it. I'll do a simpler one. Okay. Let's say there is a person of 75K inside the elevator, standing on a scale. the elevator is accelerating upwards at 1.5 meters per second squared. What is the reading on the okay. Trying to figure this out. So the elevator itself is 1,000 kilograms. The person inside it is 75 kilograms. I want to know what is the force of tension on each cable and what is the normal force or the reading on the scale of the person sitting inside the elevator. Okay, so let's go ahead and get started. Now, as you can probably tell from the way I framed this, we have two systems going on here. We have the little guy inside who is being acted on by gravity pulling him down and the floor of the elevator pulling him up. And we have the elevator, the whole elevator, which is being pulled up by 3 cables and being pulled down by gravity. So this is an L-level problem, but this is a complicated one. So let's get started. Okay, let's start with the easiest one, I think, and start with the person. Okay, so here's our free body diagram for our person. We have Fg pulling him down, and we have Fn pushing him up. Now, it's important to remember that the only thing pushing up on the person is the floor of the elevator. So that's the normal force that we're talking about here. Okay, so we have Fn and Fg. Again, Fg is simple to calculate. We have the mass of the person, 75 kilograms, multiplied by the acceleration due to gravity, 9.8 meters per second. Now, with 75 times 9.8, we have 735 newtons of force acting on that person. Now, having done that, and I know I didn't write out any summation equation before that, but by now you should just know to start by calculating Fg for everything you can even think of. All right, so now let's do our sum of forces. We only have forces in the y direction, so we can write y or not. We don't have to. Anyway, so we have Fn minus Fg, because they're in opposite directions, equals m times a. Now, the problem said that the elevator is accelerating upwards at 1.5 meters per second, which necessarily means that the person inside the elevator is also accelerating at that rate. So we can go ahead and use 1.5 for this one as well. So we have Fn minus Fg equals 75 times 2, or 150 newtons. That's how unbalanced these two things are. Okay, so if we add Fg to both sides, or 735 newtons, we end up with Fn, or the reading on the scale, being 150 plus 735, or 885 newtons. Okay, that's going to be the reading on the scale of the person inside the elevator. 885 newtons. Okay. Now let's get to our tension problem that's also included in here, and then we'll get to a mu k problem. Okay. So we have 3 forces pulling up on our elevator, 1 force pulling down, and by now we should know what to do first. What are we going to do first? What's the very first piece of math? Somebody type it in. Everybody's fingers got broke? All right. Well, either way, we're going to calculate Fg. Mass, 1,000 kilograms, multiplied by 9.8 meters per second squared. That gives us 9,800 newtons. That's our force of gravity. And we can do a similar sum of forces where we have 3 forces pulling up, and we said they were all equal, so we can just say Ft. So 3 times Ft, because there's 3 of them, minus Fg equals our mass times our acceleration. And again, it said our acceleration is 1.5. So we can plug all that in. We have this, so we can do that. 3 times Ft minus 9,800 equals 1,000 times 1.5. You can add 9,800 to both sides. Still see everything? All right. And then that gives us 1,000. Okay, 1,000 times 1.5 is 1,500 plus 9,800 is 11,300. So 3 Ft equals 11,300. Divide both sides by 3, and Ft is equal to, the Ft of any one of them is equal to 3766.6 newtons. So 3766.6 newtons. Okay. That one is a L problem. No angles, no mu k, not even any friction. So good call. Now I had a request for a mu k problem, so let's leave this on just enough for everyone to see it all at once and write down everything. And let's move on. Jose, what do you mean by type in? I don't understand. Okay, so box. Okay, box is being acted on by a force applied in this direction and a force applied in this direction. Let's call that force B. Okay, force A is 300 newtons. Force B is 50 newtons. Tug of war between a grown man and a kid, I guess. Now we're going to go ahead and say that this is along a flat surface. So we also have a normal force, a force of gravity, and we're going to say a force of kinetic friction. Okay. So since I said kinetic friction, it means this box is moving. And let's go ahead and say this is our last thing. I'll take any quick questions we can during this problem, but I got to get going in about 5 to 7 minutes. Okay. So let's get going. Let's say the mass of our box is 75 kilograms. Okay. Now let's get started. By now, again, you should know that you just start by calculating Fg. It's the simplest thing. You can almost always do it, and it's usually important. So let's just go ahead and go. Mass 75 kilograms times 9.8 meters per second squared equals 735 newtons. Okay, and because it's sitting on a horizontal surface and it's not shooting up out of the sky or whatever, in this case, which is still not always, in this case, we can say that our Fn is equal to our Fg, just in opposite directions. Okay? Okay, I left one piece out. Let's say that the box is accelerating at 1 meter per second in this direction. Okay? I just defined the direction of motion. Okay? So there we go. Now, since we've taken care of these two forces, we don't really need to pay attention to them as much anymore. So let's go ahead and get going with our summation equation. Summation of forces along the x direction. We have Fa headed in one direction, and the other two forces, Fb and Fk, are both headed in the other direction. Okay, so minus Fb minus Fk equals mass times our acceleration. And we said our acceleration is 1 and our mass is 75. We already know our force applied and our force B, so we can plug that in. So 300 newtons minus 50 newtons minus whatever Fk turns out to be equals 75 times 1. Okay, so combine like terms over here, 250 newtons minus Fk equals 75. Now, if we move Fk over and move 75 this way, we have 175 newtons equals Fk. Okay. If you're in L, this is where you'll stop, because we just figured out what our force of friction is. But if you're in K, we're going to work out what our mu K is. Okay. Now, our mu K equation is Fk is equal to mu K, that's the Greek letter mu, multiplied by our normal force. We've already calculated our normal force, so we can plug that in here. And in fact, we already know our Fk. So let's plug all that stuff in. 175 newtons is our force of kinetic friction, equals whatever our mu K is, multiplied by 735. Handwriting's even bad at home. 735 newtons. If we divide both sides by 735 newtons, okay, so actually, Jose, you see how the sign on FB and the sign on FK are both the same? So since FK and FB are in the same direction, they have the same sign, and they would add up. It's just that we didn't know Fk until later on in the problem. We had to solve for it. Okay. And then we wanted to do other things with it, like solve for the mu K. So I needed to solve for Fk first. Does that clear up the issue? All right. So let's go ahead and do this math. 175 divided by 735. And our mu K is equal to 0.24. Okay. Now, y'all have exactly, let's say, 1 minute to ask me questions that I can answer quickly, or I've got to get going. Go. Well done, Jada. Well, 0.238. So I rounded up to 0.24. Okay, quickly. Y'all got like 45 seconds left to type some questions at me. Okay, fair. Well, either way. When would you use the cosine thing? Okay, you would use the cosine thingy whenever you have an angle that is not 180 degrees or 0, right? Anytime we're just block on a horizontal plane, this is either 0 or 180 degrees. And in that case, your cosines and sines are just equal to, like, cosine of 0 is just 1, and sine of 0 is just 0. So we kind of do cosine and sine in every problem. It's just that we don't see it. We don't see the effects of it when the surface is horizontal. So we'd only ever do it when the angle was something other than 180 or 0. Okay? And then, like in this case where we have FG pointed down, we would draw our fake triangle, and the way we draw our triangles, this angle here is always equal to that one. All right. If you draw your triangle some other way, that might change. But if you draw your triangles the way I drew my triangle, with the right angle there, these two will always be equal. Okay. When working with angles, will you always use force parallel and perpendicular? Okay. So that can be equal to that can be equal to that, whatever. I call them force parallel and perpendicular because it's convenient for me. So this force right here that sort of extends through is perpendicular to the face of the ramp. And that's why I call it force perpendicular. It's the only reason I do it. There's no inherently right way to do it, but it helps me stay on track. Likewise, when we have our force of gravity pushed down, we have a piece that does that. And this is always going to be parallel to the face. So doing a force perpendicular and force parallel, those just help me stay clear as to what part of the force I'm looking at. So you guys can use anything else you want, but I do always use force parallel and perpendicular when I do angles in this way. Right now, if it were horizontal, but I had something that was just above horizontal, in this case I'd probably use fx and fy, because there'd be a part of this that would be pointed in the x direction and a part of it that would be pointed straight up. So in that case I'd probably use fx and y. But on an inclined plane, I myself will always use f perpendicular and parallel. Okay, last question, guys. Does the static force always go in the direction of the pull tension force? I assume you mean Fs, or the force of static friction. Okay, friction is always in the opposite direction of the movement. So whichever direction the box is moving, if the box is moving this way, then friction is that way. But if the box is moving this way, then the friction will be that way. And that's true for static or kinetic friction. Friction resists the movement. Whichever direction the movement is pointed, the friction will be in the opposite direction. Okay, so guys, deep breaths. Deep breaths. Every single question on the test is solvable. Okay, make sure that you keep straight that force is in newtons, mass is in kilograms, acceleration is in meters per second squared, and mu's are unitless. All right, so if you're given something that says 150 kilograms, you cannot put it as a force. You have to do something else to get it into a force. You have to multiply it by an acceleration in order to get it a force. So if you keep all your stuff straight and remember the two main equations that we have that were different than stuff we learned before, these two equations, you guys should do just fine. Okay? I hope this was helpful, everybody. Don't forget to try to get your extra points if you're here for that. I hope this was helpful, and I'll see you in class.